Let's see this problem. This problem says hemispherical ball of radius r. Its radius r is rotated about its axis of symmetry, which is vertical. That means this is a spherical ball, hemispherical ball. It is rotating on its vertical axis. A small block is kept in the bowel at a position where the radius makes an angle theta with the vertical. That means this is at a position where with the vertical it makes an angle. The block rotates in the bowel without any slipping. That means block neither slips down nor it slips up. The coefficient of friction is given mu. Find the range of angular speed so that the block will not slip. You know, we have seen in earlier problems that if in such cases the ball rotates too slow, then the block will have a tendency to slip downward. And if it rotates too fast, the block will have a tendency to skid upward. So anyway, there is a range in which range of angular velocity the block will not slip. We have to find out that answer. So let's see how we do it. Let us first find out the higher limit of angular velocity omega. Let's first take this case. That means in this case, the block is beyond this omega, the block will have a tendency to slip up. So we write here for understanding, beyond this omega, block upward. And then we write the force equations. Say the block is here. Say the block is here. Then what are the forces? This has a force mg vertically downward. And this has a force square by r, which is horizontal. Or rather, since we have to find out the angular velocity, we write it in the form of omega. Omega, that is m omega square r. Is r? R is this radius. Mind it, r is not the radius of the ball. R is the radius of rotation. Right? Now, there is a slope. Let us exaggerate the zoomed in value. There is a slope along the ball. And if there is a slope along the ball like this, then, and this is, if we draw a perpendicular to this is mg cos theta. Mg, because it says the block makes an angle theta with a vertical. This is mg cos theta. Now, and this force, downward force, is mg So mg we have split into two perpendicular components. Similarly, m omega square r also is split into two perpendicular components. This will have one component in this direction, which is m omega square r n theta, and a component in this direction, which is m omega square r m omega square r cos theta. And this force is the reaction force R. And if this is the reaction force and the block is going to have a tendency to slip upward, so there is another force, frictional force downward, which is mu R. These are the forces. As we have seen already earlier in many cases, the trick is to find out and show all the forces acting on the body and then resolve them into perpendicular components. Because, perpendicular components or perpendicular vectors, they don't act on each other. Now, what do you do? We consider the forces along the slope. So this is a symbol which I have used to show you that I am considering the forces along the slope. Forces along the slope, I find m omega square r cos theta, m omega square r cos theta will be equal to opposite forces mu r and mg sine theta is equal to mu r plus theta. Then I use, this is another symbol I use for you, that I am now considering the forces along the normal to the slope. When I consider forces along the normal to the slope, what I find R is on the normal upward side, and downward side, there are two forces, m omega square r sine theta and mg sine theta. So I have m omega square r sine theta, m omega square r sine theta plus mg is equal to the normal reaction force R. Capital R is the reaction force, small r is the radius of rotation. Let us consider that this as equation 1 and this as equation 2. Right? And equation 1 and equation 2. Now what you can do, so there is one thing we should remember, that this is smaller, this distance is smaller, and radius r is the radius of the entire ball, and this angle is theta, and this is also radius of the ball, which is r. So small r is equal to capital R sine theta. This is another thing we must remember. Small r is equal to capital R sine theta. I should do one thing. There are capital R is the radius of the bowl. So here I should not take R. Here I should take let me take this as n, this as n, or the normal reaction force. Let me take this as n. And in that case, I should change this also by mu n, and this also as mu n. Otherwise, there will be confusion. This is mu n, and this also as the reaction force n. Now, what do we do? We put the value of n into equation 1. So, put the value of n from equation 1. We'll find that equation 2 says this n, in equation 1 says m omega square r cos theta. So we get m omega square r cos theta is equal to, is equal to mu, value of n we put from here, m omega square r sin theta plus mg cos theta, that is mu n, and then I have mg sin theta plus mg, then I have mg sin theta. From here, what we get? We get m omega square. Now, this small r is capital R sin theta. Capital R multiplied by cos theta is equal to mu multiplied by m omega square r, m omega square. This small r is again equal to capital R sin theta. So it will be capital R sin squared theta. Capital R sin squared theta plus mu mg cos theta, mg cos theta plus m sin theta. Here, all the m gets cancelled. M gets cancelled. So now if you do a little bit of workout, which I'm going to avoid in order to save time, you'll find omega will be equal to mu multiplied by mu cos theta plus sin theta, whole thing divided by r capital R's sin theta, and this multiplied by cos theta minus mu sin theta, and this whole fraction whole to the power half, that means under. So this is the hard limit of angular. Similarly, if we want to find out the lower limit of angular velocity, this is now it will be easy. The lower limit of angular velocity, similarly, this is m omega square polar. This is mg downward, and along the slope, component of m omega square is m omega square small r cos theta, and perpendicular to the slope, the component of, if we draw this way as parallelogram, that will be easy to remember. This is m omega square r sine theta, sine theta. And mg also will have two components. One component is down the slope is sine theta, and another component in this direction, this is mg cos theta, and this is the reaction force N. And this time, the friction force works upward. This is mu N. Friction force was upward because this is, we are trying to find out the slowest speed, so that if it is slower than this, then the body will slip downward, so there will be friction force upward. Similarly, here, if we consider the forces along the slope, this force is m omega square r cos theta, m omega square small r cos theta, plus upward force is mu n, will be equal to downward the slope force mg sine theta, mg sine theta. And if we consider the forces perpendicular to the incline, then we have this normal n is equal to mg cos theta, this force, mg cos theta plus component of m omega square is m omega square small r. Here we have two equations. So remaining solution is same. Also, do not forget, small r is equal to capital R. If you find out the value of omega similarly, that means put the value of n from here to here, then you will find omega is equal to g sine theta minus mu cos theta divided by capital R sine theta within bracket cos theta plus mu sine theta, whole thing whole to the power half. So this is the minimum angular velocity, and this is the maximum angular velocity. So this solves this problem. Let's go to the next problem. This problem is not a difficult problem, but I thought I must show you the answer because it may be difficult for some of you to understand the problem. Here it says a particle is projected with speed u at an angle theta with the horizontal. Actually, here in this circular motion chapter, we have a projectile problem that may lead to a little confusion. So I thought I must solve this problem for you. So here it says that a body is projected upward in a projectile motion like this, and the velocity here is u and at an angle theta. These are the two values given. Then it says, consider a small part of its path near the highest position and take it approximately to be a circular arc. What is the radius of this circle? It is true that when it reaches the topmost point, although the curve is parabolic, but from your knowledge of geometry, you know that very near to the peak of the parabola is actually, you can consider it as approximately a circle. So they want to know what is the radius of curvature. Let's say this radius of curvature is r. Now here, now when the body is here, what is this? Is this horizontal velocity? If horizontal velocity of the projectile is u, so this velocity is u cos theta. Why? The horizontal velocity from the projectile chapter, horizontal velocity does not change. In a projectile, there is external force of only the force of gravitation, which is vertical. And that is why in a perpendicular horizontal direction, the gravity or any external force does not have any action. So horizontal, so we can write horizontal component that is u cos theta remains constant all through its flight, u cos theta. So now if you consider this as a circle and it has a tangential velocity u cos theta, then what is the centripetal force? Centripetal is equal to mv square by r. R is the radius of the circle we have considered. This is equal to m u square cos square theta by r. Now, who provides this centripetal force? We write this force is provided by mg, because there is nobody else here around this projectile to provide a downward force. Therefore, so you can write that cos square theta, m u square cos square theta by capital R is equal to m gets cancelled. From here we get R square cos square theta by G. So the radius of the curvature very near to the topmost height is u square cos square theta by G. Now there is a second part of the question. What is the radius of curvature of the parabola traced by the projectile at a point where the velocity makes an angle theta by 2 with the horizontal? Now see, this is, let me draw this once again as a little bigger diagram. The projectile goes up like this and moves in this direction. At this point, this is u, and this angle is theta. At some point, let us consider the tangential velocity becomes tangential velocity v, right? And the angle here has been reduced. Let's say this angle is theta by 2. Now, what is the horizontal component of this tangential velocity? Horizontal component, let's say this point is A. And A, horizontal component of tangential velocity is equal to v cos theta by 2. And this has to be equal to u cos theta because we have already seen that horizontal component of the velocity remains same. Also, for your remembering this, I write down. Also, horizontal component of velocity it does not change. Does not change. So what we can write? So we can write u cos theta, the horizontal component at the beginning, will be equal to v cos theta by 2, where v is the velocity at that particular point that we are trying to discuss. Also, here, at this point, the centripetal force is mv square by r. This is mv square by r. R is the radius of curvature here that we are trying to find out. R is the radius of curvature. Also, mv square by r is the centripetal force. Centripetal force. Who will provide this centripetal force? Who provides this force? Provides this force? The answer is the component mg in that direction. Here, now we try to draw the mg. This is mg. This is mg. And this angle is theta by 2. So the component of the mg in this direction is mg cos of theta by 2. Cos of theta by 2. We find m v square by r is equal to mg cos of theta by 2. M and M gets cancelled. M and M gets cancelled. And what we have, therefore, R is equal to V square divided by G cos of theta by 2. V square G cos of theta by 2. And also, we use this equation, U cos theta is equal to V cos theta by 2. So, from here we can write from here, we go back to here, V is equal to u cos theta divided by cos theta by 2. Now from here, we bring the value of v here, v square. So it is equal to, so it will be equal to u square cos square theta divided by, denominator will be cos square theta by 2, whole thing multiplied by this g cos theta by 2, 1 by g cos. So that is equal to, in numerator we have u square cos square theta, u square cos square theta. In denominator we have g multiplied by cos cube theta by 2. So this is the radius of curvature at the point A, where the point or the tangential velocity makes an angle theta by 2. So we shall see the next problem next time.